So, good afternoon, everyone. My talk is about the mode 2 crack propagation problem within the generalized continuum theory of coupled stress elasticity. Now, the primary goal in this work is to study the microstructural effects in dynamic crack propagation. And we model the microstructure with the generalized continuum theory of coupled stress elasticity, which is one of the simplest gradient type theories. Now, so the plan of the presentation is as follows. First, we will tell some words about the motivation for considering crack propagation problems within the context of coupled stress elasticity. Then we will very briefly present the fundamentals of the dynamical version of the theory, and proceed with the study of with the study of Rayleigh waves in a coupled stress medium, and examine how the microstructure affects the limiting Rayleigh speed. Then we will continue to study the mode 2 steady-state crack propagation problem using the analytical technique, the analytical Wiener Hopf technique, and present some results about the dynamic stress intensity factor and the dynamic energy release rate. So, now it's well known that in complex materials, the resistance to fracture depends strongly upon the microstructural features such as the grain size, the number of inclusions, and the porosity. For example, it has been experimentally observed that in ceramic materials, in cracked ceramic materials, that the energy release rate depicted as gamma in this figure decreases as the flow size, the size of the crack, becomes comparable to the grain size, as we can see here. Now, this is clearly a size effect which cannot be predicted by classical linear elastic fracture mechanics. Thus, it becomes apparent that for a proper description of the fracture processes, the proposed approach should introduce length scales in order to capture the pertinent size effects. As we said, unfortunately, the classical linear elastic fracture mechanics includes no internal length scales and thus is unable to predict and capture the observed size effects. There are also other experimental studies that show deviations from the predictions of classical elasticity. For example, an atomistically sharp crack has been observed at the interface of a single crystal between an niobium and sapphire interface. Also, stronger singularities of this type have been observed in dynamic crack initiations. As we have said, these phenomena cannot be modeled through the classical length. On the other hand, we know that generalized continuum theories are able to capture the size effects by enriching the classical continuum with additional material length scales. Through the last years, generalized continuum theories became popular and have modeled many problems successfully, such as size-dependent indentation, modeled foams, porous solids, thin films, and also fracture of cellular materials. Now, knowing the limitations of the linear elastic fracture mechanics, and based also on our previous experience on static problems in generalized continuum theories, we aim in this work to extend our study to dynamic problems, using as a first step the simplest theory, the simplest generalized continuum theory, the theory of coupled stress elasticity. Now, if a continuum with microstructure is viewed as a collection of subparticles, the kinetic energy takes the following form. In dynamic coupled stress elasticity, also known as Kossara elasticity with constrained rotations. Now, the first term here is the classical inertial term that we have also in the classical theory, and the second term involving the spins is the microinertia term, which is not encountered in the classical theory and reflects the more detailed description of motion in the present theory. As for the kinematical description, we have the following quantities in the framework of a geometric linear theory. You have the usual strain tensor, the rotation tensor, and the rotation vector, which are fully dependent upon the displacement vector in the constrained Kossara theory, and the curvature tensor defined as the gradient of the rotation vector. Then the balance laws for the linear and irregular momentum, if we ignore body couples and body forces, take the following form, where capital tau and capital M is the force traction and M capital is the moment traction. Moreover, yes? Yes.
So this is not classical Kossara.
No, it's constrained Kossara.
But you know, it is still posed in dynamics.
No.
Based on inertia, we can count with this.
What?
No, things tripping.
No. for the problem, for the steady state problem that we consider here, everything is objective. There is no problem. There is a problem of objectivity if you consider the general case, but for the steady state problem considered here that I was going to show, there is no problem of objectivity. So capital tau and capital M is the force traction, and M is the moment traction. Accordingly, the stress and coupled stress tensors are defined in the following way by considering the equilibrium of the material tetrahedron, and also we have, and from the balance equations we can obtain the equations of equilibrium. Epsilon here is the Levi-Civita symbol. Now, assuming a linear anisotropic material response, we have the following form for the strain energy density. The terms appearing in red are the new terms in coupled stress elasticity related to the curvature. And accordingly, we can define the constitutive equations of the theory relating the symmetric part of the stress with the strain and the deviatoric part of the coupled stress with the curvature tensor. Eta and eta prime here are the new coupled stress moduli. Now, the equations of motion in terms of displacement are the following, fourth order PDEs, and here we see the equations for the dilatation and the rotation, where L here and H are the two characteristic material lengths, the first one related with the strain energy density and the second one related with the macroinertia of the continuum. Now, we observe that the dilatation is governed by the same second order equation as in the classical theory, whereas the rotation vector is governed by higher order PDE. Now, in the limit, all the equations tend to the classical Navier-Cauchy equations, to the classical linear isotropic elasticity equations. Now, the fact that only the rotation is governed by a higher order PD means that the pressure waves and the dilatation by the classical equation means that the pressure waves in coupled stress elasticity are not dispersive. Indeed, by considering time harmonic plane wave solutions to the previous equations that we saw, we obtain the phase velocities for the pressure waves, which are the same as in the classical theory, and for the shear waves, where we see that the velocity of the shear waves depends upon the wave number of the wave number C. So we see that only shear waves are dispersive. In order to investigate further upon the dispersion relation of the shear waves, we consider the group velocity at which the energy propagates in a dispersive medium, and you cannot see it clearly here, and we distinguish the following three cases. The first case is when the term in the brackets is negative, so the group velocity is less than the velocity of the shear wave, so we have normal dispersion. The second case is when the bracket is positive and we have anomalous dispersion, and when we have the special relation here that makes this bracket equal to 0, we have no dispersion at all. Now, in the case of plane strain, that is also our case, the case of interest here, the differential equations, we obtain the following system of differential equations, a coupled system of the fourth order relating the ux and uy displacements. Of course, this system is much more complicated than classical theory. However, uncoupling can still be achieved by use of the Lamé potentials. And we can show that we have shown that this representation is complete. In this way, we obtain from these equations the two field equations of the problem, the uncoupled now for the phi and psi Lamé potentials. Now, in order to study the propagation of Rayleigh waves, we consider plane wave time harmonic solutions to these two equations. So we have these two solutions, where xi is the wave number and w is the frequency. Also, capital A, B, and C are the wave amplitudes. Now, these equations, these solutions, combined with the traction-free boundary conditions for a half space in coupled stress elasticity in terms of the Lamé potentials, lead to an eigenvalue problem for the wave amplitudes A, B, and C, which accordingly provide the dispersion equations and the phase velocity of the Rayleigh waves for a material characterized by coupled stress elasticity. Now, as we see in this graph, here we see the variation of the normalized phase velocity with respect to the classical shear wave velocity versus the normalized wave number. This is not a subscript, this is psi multiplied by L. Actually, I don't know why it shows here in this way. So what we see here is that for small, very small wave numbers, low frequencies, the phase velocity of the Rayleigh waves is equal to the classical value which means that the waves do not see the microstructure, cannot see the microstructure. However, as the wave number increases, we see marked deviations from the predictions of the classical theory. In particular, we distinguish two cases, depending always on H0, where H0 is the ratio between the two characteristic material lengths, the two competing characteristic lengths. The H, which is related to the microinertia, and L, which is related to the strain energy density, and in particular to the curvature contribution to the strain energy density. Also, H0 star here is a special value defined as the ratio of the classical Rayleigh wave velocity to the classical shear wave velocity. Now, so we distinguish the following cases. If H0, the ratio between the two microstructural lengths, is less than the special value, is greater than this special value, then the phase velocity of the Rayleigh waves in coupled stress elasticity becomes smaller than the classical Rayleigh velocity and tends to a constant value that depends upon H0, upon this ratio. On the other hand, when H0 is greater than this special value, less than this special value, the phase velocity of the Rayleigh waves increases above the classical velocity and reaches a constant limit that depends on the Poisson ratio. Now, based on the previous results, we can now define the range of the sub-Rayleigh regime, because our crack will propagate with a constant velocity and with a constant sub-Rayleigh velocity. As here in this graph, we see the sub-Rayleigh regime. M here is the normalized propagation velocity. V will be the velocity of the crack, normalized with respect to the classical shear wave velocity. In general, a motion is characterized as sub-Rayleigh as when the propagation velocity is smaller than the velocity of the Rayleigh waves in coupled stress theory. So again, we distinguish two cases. When H0 is smaller than the special value, it suffices for the crack to travel with velocity less than the classical Rayleigh velocity. However, when H0 is above the special value, the limiting Rayleigh speed is less and depends upon H0. So now we can proceed to study our problem, which is the mode 2 steady-state crack propagation problem. As I have said in the beginning, we study a steady-state problem, so the inertia terms, actually, the problem, it's not transient, so we can have the microinertia, it's not a transient problem. Through the Galilean transform, we eliminate time from the equation, so there is no problem of objectivity. In fact, we have a body of infinite extent, and we have a semi-infinite crack subjected to a exponentially shear decay loading at the crack faces. L is the geometrical length, and the crack travels with a sub-Rayleigh velocity through the medium. Now, due to the steady-state nature of the problem, we use the Galilean transform and we eliminate time from our equations in this way. So in the new moving coordinate system now, x capital and y capital, we have the following boundary conditions and field equations describing our problem, the mode 2 problem. So this is a mixed boundary volume problem now that we have to solve. There is something also here that it does not appear for some reason. So we want to solve analytically this problem. What we're going to do is to use the Fourier transform in order to find the solution, and in particular we define the unilateral Fourier transforms of the unknown stress ahead of the crack tip and the unknown crack face displacement in the following way, where sigma plus is analytic in the upper complex domain, and U minus, which is the transform of the crack face displacement, is analytic in the lower complex domain. Now, from the solution of the field equations and the enforcement of boundary conditions, we derive the following functional equations in the transform domain, as we see here, which connects the two primary unknowns, sigma plus and U minus. So in order to solve this equation, one equation for two unknowns, we will use the Wiener Hopf technique. And in order to do so, we have to decompose the functions appearing in red to analytic functions in the upper and lower half planes. So, and the function, in particular, the kernel function n, defined here, is decomposed using a multiplicative decomposition of this form, where the n plus and n minus functions are obtained using Cauchy's integral theorem, Jordan's lemma, and also taking into account the branch cuts of the kernel function n. So these are the n functions, n plus and n minus. In this way, and applying the Liouville's theorem, we can derive the final Wiener Hopf equation, and then employing Liouville's theorem, we can find the transformed expressions of the shear stress ahead of the crack tip and the crack face displacement, which are these expressions here. Now, actually, we have solved the problem, since we have these two equations, and we can find the stress ahead of the crack tip and the crack face displacement by inverting, by using the inverse Fourier transform. Also, utilizing the Abel-Tauber theorem, we can obtain the following near tip field, where we see that the shear stress ahead of the crack tip and the crack face displacement have the same asymptotic behavior as in the classical theory. However, the detailed structure of these fields is of course different in the coupled stress theory. Now, the important thing is that also we can find the dynamic stress intensity factor. The important thing here is that, contrary to the classical elasticity case, the dynamic stress intensity factor in the coupled stress theory of elasticity depends upon the velocity through the function n plus. Where in the classical theory, the stress intensity factor is for the steady state problem that we consider here, the modes to steady state we consider here, is independent of the crack tip velocity. Now, in this graph, we see the variation of the displacement, of the crack face displacement at a specific point along the crack faces. In coupled stress elasticity, which are the solid black lines, and in classical elasticity, with respect to the normalized velocity of the crack. So what we see is that as we approach the Rayleigh velocity, here, the pertinent Rayleigh velocity, the displacement in classical theory becomes unbounded, while in the coupled stress theory increases significantly, but always remains finite. Also, we know that since the red line is above always the solid black lines, the displacements in the coupled stress theory are smaller than the respective ones in the classical theory, which shows the stiffening effect that we find using coupled stress theory. Now, in this graph, we see the variation of the shear stress ahead of the crack tip, and we observe for when the speed of the crack approaches the Rayleigh velocity. We see that with the dashed dot line, we see the asymptotic solution, which dominates within a zone of half the characteristic length, and the analytical solution, which is significant, as we see here, up to 2 times the characteristic material length. After we move away from the crack tip, more or less, for this kind of material properties, we take the classical solution as we see here, so the 2 lines almost coincide. Whereas here we see the variation of the coupled stress ahead of the crack tip, again for 3 velocities, when m goes to 0, so the crack does not move, and when for the third curve is when the crack moves with reaching almost the Rayleigh velocity. What we observe here is that at the crack tip, the coupled stress is bounded at the crack tip and increases, reaching a bounded maximum, and then diminishes quickly to 0. 3. Okay, here we see the variation of the stress intensity factor, the variation of the dynamic stress intensity factor to the static stress intensity factor. What we see here is that as the crack approaches the Rayleigh limit, we have again a significant increase, and we see that case 1 and 2 that corresponds to an H0 which is smaller than H0 star. The Rayleigh limit is the classical Rayleigh limit. However, when H0 is greater than H0 star, curves 3 and 4, the curve stops earlier, since this is the new Rayleigh limit, the coupled stress limit, which is less than the classical one. So finally, we examine the energy release rate. The general expression, the J integral for the dynamic J integral takes the following form, which is path independent for the steady state, only for the steady state considered here. And we evaluate this integral by considering a rectangular shaped contour surrounding the crack tip. In this way, we can use only the asymptotic fields that we have analytically around the crack tip. And here we show the analytical expression for the J integral in coupled stress and the classical theory. We'll skip that. Now, in this graph, we see the ratio of the J integral in the coupled stress theory to the J integral of classical theory. What we see again is that we distinguish 2 cases. When H0, the ratio of the 2 characteristic lengths, is less than H0 star, the ratio decreases monotonically. And as we approach the Rayleigh limit, it becomes 0. And this is because the classical elasticity predicts an infinite energy release rate at the Rayleigh velocity. However, the energy release rate of coupled stress elasticity is still finite. A different behavior is observed when H0 is greater than H0 star. So we see that as H0 increases, the ratio becomes, in the end, an increasing, a monotonically increasing function of the velocity, and stops at each time at the pertinent Rayleigh limit. So for each curve, this is the Rayleigh limit. For the Rayleigh limit is somewhere here. So the last figure shows the ratio of the energy release rate in the coupled stress theory to the classical theory, but this time with respect not to the velocity, but with respect to the characteristic material length L, small l, that is related to the strain energy density, and normalized with the capital L, which is the geometric length induced by the loading. What we immediately observe is that when coupled stress effects are taken into account, there is a decrease in the energy release rate. And this shows that coupled stress elasticity predicts a strengthening effect, since we have a reduction of the crack driving force, which is the J integral, and that takes place as the material microstructure becomes more pronounced. And this reduction is more evident as we approach the Rayleigh limit. On the other hand, we see that when the characteristic material length is 0, so we are here, the ratio of the energy release rates is equal to 1, which means that we have a continuous transition between the coupled stress and the classical theory as far as the energy release rates are concerned. So, and this find actually explains the first graph that we saw in the beginning about the cracked ceramic and about how the energy release rates decreases when the flow size of the crack in the ceramic material is comparable to the grain size. This actually, so this shows analytically how this happens when these become comparable. So our main purpose here was to gain a deeper insight into the physical mechanism of dynamic fracture of microstructure materials when these microstructure materials are modeled by coupled stress elasticity. Now, depending on the values of the microstructural ratio H over L, we have seen that the actual limiting Rayleigh velocity can be much lower than the classical value predicted by the standard elastodynamic theory. We have seen also that both the stress intensity factor and the energy release rate depend upon the crack speed. And as the crack speed approaches the pertinent Rayleigh limit, both quantities increase significantly but always remain finite. Whereas in classical elasticity, the respective stress intensity factor does not depend upon the crack speed, and the energy release rate becomes infinite as we approach the Rayleigh limit. Finally, we have seen that the energy release rate in coupled stress elasticity decreases monotonically as the material microstructure becomes more pronounced. So, in this way, coupled stress elasticity predicts a strengthening effect, since we have a reduction of the J integral of the energy release rate as the material microstructure becomes more pronounced. Thank you very much.
Thank you. Are you assuming the compatibility condition of strain and rotation?
Yes, yes.
Throughout the process?
The kinematical compatibility conditions about, yes. Coupled stress elasticity, yes, considers it.
But so when there is fracture, the compatibility conditions are no more satisfied?
Yes, but locally at the crack tip and the crack faces, yes. But I mean, but this is, I mean, the same problem also appears also in the classical fracture mechanics. I mean, the compatibility, but still, I mean, this is.
So they are satisfied in the solid itself, but at the crack faces, so there is incompatibility of both the displacement and the rotation.
Particularly, the rotation here is along the crack faces is 0. I mean, due to the anti-symmetry of the mode 2 problem. But for the mode 1, yes, we could have also rotation. But this is, I mean, a standard, I mean, problem of classical fracture mechanics. I mean, on the crack face, you do not satisfy the compatibility. I mean.
As best as I can tell, you were using the Rayleigh gauge velocity versus the crack velocity, and yet your dispersion is not trivial. You have a dispersive medium above a certain threshold. Is it conventional to do that, or
is it
conventional to do this, or would you ever use the group velocity? Energy propagates the group velocity. That's why I asked. So would you compare the Rayleigh group velocity to the crack velocity? Is that more appropriate?
So you're saying that instead of comparing the Rayleigh velocity, the Rayleigh limit, to compare the group velocity?
Well, you talk about the velocity.
Yes, we have a crack that propagates in the sub-Rayleigh regime. So, I mean, it's natural to compare it with the Rayleigh limit. I mean, this is what happens. This is the usual procedure in fractional mechanics. When they say about subsonic or sub-Rayleigh crack propagation, they compare it with the Rayleigh speed, with the pertinent Rayleigh speed, always.
I guess the point is the Rayleigh speed is ambiguous. You can have a phase velocity or you can have a group velocity. The energy is traveled with the group velocity, not the phase velocity. Just like when I talk about band gap.
Sure, the energy in the displacement medium travels with the group velocity, but from the mathematical point of view here and from the physical also point of view, the natural selection, I think, is the Rayleigh velocity itself.
I don't say the group velocity is the physical velocity.
For example, the distinction that they made in classical fractional mechanics, I mean, is that when you go above the classical Rayleigh limit or below the Rayleigh limit, I mean, this is how you distinguish the sub-Rayleigh or the super-Rayleigh regime. This is the selection, I mean, that they made, I mean.
So I can have a wave that has non-zero phase velocity, but it will have zero group velocity.
Sorry?
I can have a wave that doesn't propagate that has a non-zero phase velocity. Phase velocity is not a physical meaning. Now, if it's not dispersive, group velocity and phase velocity are equal.
Yes, are equal, yes. No, here they're not equal because it's dispersive.
I think it's physically more correct about that.
No, but also if you consider the mathematical procedure, because we use this analytical technique of the Wiener Hopf technique, breaks down if we pass the Rayleigh limit, the classical Rayleigh, the pertinent Rayleigh limit in coupled stress theory. So the whole mathematical procedure does not apply the moment that the speed exceeds the Rayleigh limit, the pertinent Rayleigh limit. So, I mean, also mathematically, this is the physical selection.
You have dispersion before this happens, correct?
I have dispersion?
You have non-trivial dispersion before this happens, before you have this breakdown. And in that case, you should use group velocity.
Okay, but yes.
Yes, you refer to two papers. One by Clinton,
Sorry?
the other by the Wagner. But these people, that's the typical case. They study what really is a cost factor. Constraint on the internal rotation. That is a model.
Yeah, but so you mean that so your point is that the point is that what you're trying to say is that because I didn't get can you repeat your comment?
You refer to two papers.
Yes.
Okay, one by Pinton and his colleague, and the other by Modell and Marquez.
Yes.
They don't relate to this case.
No. These papers are that's why I've written them not for the general dynamic case. They consider a static case.
That's the point. But they don't consider the constraint theory.
No. Lombard and Marquez-Koff consider the constraint.
The real cost factor.
No, but also Lombard and Marquez-Koff consider. No, yes, of course, yes. And also Atkinson considers the special case, yes.
In what expression?
This one.
Because in this expression only the gradient is involved.
Only?
This
Yes.
distress
Yes.
captures the gradient effects automatically from its very structure. So you don't see the internal rotation, you see only the gradient of the rotation.
But
It's the same moment which you did in between.
no.
Yeah?
But however, both Atkinson and Lepkin and Lombard and Marquez-Koff,
There is no problem with the boundary condition.
there is a problem of boundary. That's what I said because you said in the beginning, when you take this part of microinertia in the kinetic energy, indeed you have, for a transient case, you would have problem of objectivity. Because this go also in the boundary, but here we consider only the steady state case. So in the steady state case, I mean also Jan James has shown that in the steady state case, these terms do not cause a problem, only the steady state case.
I would prefer a theory which is also valid in the dynamic case.
Okay, I mean, in the dynamic case, you can treat those terms as, I mean, there is a procedure for the field equations to treat them as body forces or to take them in the body forces. There is a procedure. But here, we didn't have any problem, and I didn't go into this matter because here we have the steady state case. And use the Galilean transformations and the time goes away, I mean.
But if you say that I have the Newton equation when there is no acceleration.
No, but this is a dynamic problem. It's not a static problem. Yeah.
Right at a certain level of disagreement.
Yes.
Does